7.3 is about now. Originally, you have a plane wave in the infinite medium. Now the consideration is if you have two media, they just separate by a infinite interface, infinite plane. So you have plane. So you have two medium. I think that's called mu. You have permeability mu and epsilon on one side, and then the other side mu pi, epsilon pi. Okay, and you define your coordinates. The phase interface actually between the two media is on actually the what we call the z equals 0 surface. This is z equals 0 because you define this as your x. What the x-axis, and this is the z-axis. So this is the blackboard is the xc plane. Okay, and this is later on we'll identify as a so-called plane of incidence, which means the wave vector will stay within this plane. The wave vector doesn't come out. Doesn't have a y component. Basically, this your x, the y will be going in because according to the y telling you x and y. X cos y gives you z, so y is going in. So y is going in. Okay, so that is the geometry between the two media. All right. Now the consideration is you have a plane wave, the incident wave from below, from negative z, and propagate in the positive z direction and positive x direction. So you have a wave vector. So basically, you write it by convenient, you point it at the origin. Okay, and this is a. Okay, and then it make an angle called incident angle. Angle I here. All right. Now this wave has a electric field, magnetic field. So the direction will specify later. But for now, it's just saying that you have an E and B here. Original E and B. This incident plane wave with this wave vector K. All right. Then after you get into the interface and go into the other medium, then generally the wave vector will change, the electric field, magnetic field will all change. We'll say whatever the angle is Jackson. So it will go into another wave vector. I think Jackson called K pi. Wait, yeah, K pi, and make the angle R, which is refraction. All right, so also good. And then it has the electric field E pi, magnetic field E pi. I mean, EB are oscillating with omega, because omega, obviously the omega doesn't change. Still, because it's still the single frequency, right? But then the interface can induce a refraction, also refracted back, so they propagate back to the negative z direction, but still along the positive x direction, because in x direction doesn't encounter any interface. The medium is still the same, so along the x direction doesn't change. So the wave vector change direction in z, but not x. Generally, you have this refracted wave vector is K double pi, that's called it. And then you have this angle. Now it's a refracted angle, and so it still starts from R, but Jackson called R prime, which is not a very good notation because the upper medium you already used the pi for that. This angle is R pi, so So you need to be a little careful. But this is more acceptable because we will right away derive the property that the alpine is as I. We later on just identify this as I, good, because you all
reflected
from this interface. There's an infinite plane that's going out. So this is an infinite plane on this zero zero.
So if it's reflected, shouldn't the incident and the reflected angle be the same?
Yeah, but we need to divide that. Okay, we need to divide that. So this is just to show you how to divide that. Okay, and you divide that by matching boundary conditions. Okay, you have two medium, two media. So you need to match the boundary condition of all this electric field, magnetic field along the zero plane. And once you require that they satisfy the boundary condition, then you can first divide all this geometric optics property. What they said, the refracted angle is the same as the incident angle, and then the Snell's law, which you will see right away. Okay. So now we have B double I, B double P, and still oxidating. Okay, so that's all the notation and the geometry. All right, then now you can write down explicitly what these fields are. Right? After you write it down, then you now require them to satisfy boundary condition, which you also write it down explicitly. Okay, so the E is, I think just you just use E sub zero. Yeah, E sub zero. Just just I mean amplitude vector E sub zero, and the direction is not specified yet up to here. So that's the phase and okay, so that's fine. And now the magnetic field E is we figured that out by the easiest one is the the Faraday's law. The Faraday's law is there's you have curl E. Faraday's law E is minus positive B positive T. And with this form also the same phase factor in B. So curl E giving you the basically is K cos, pull our IK out. IK cos E, but then this pull out the minus I omega. So I and I cancel and minus I cancel. K cos E equals to omega B. This for this phase factor. Okay, so B would be equals to K. The same. Yeah, you need to K cos E sub zero. K cos E and divided by omega. And I should be more careful. This one is but that's fine. This is still the incident rate, so this is still the same K. Right, that's fine. Okay, so and then we can be more specific about the relationship between K and omega, which we already defined or derived. So K over omega or omega over K is the speed, which is square root of it's actually should be 1 over. This is the phase velocity. So it's 1 over square root. This is in this medium view, right? And yeah, And we can later on define the, actually we define already in the, so in the index of refraction, so that we define in 7.5 C divided by N. Oh, the C divided, C is just square root of the C over N. C is just 1 over epsilon 0 mu 0 square root of epsilon 0 mu 0. So N is just defined as mu 0 epsilon 0. Right. Just put M on the other side divided this. Right. And this. Right. C is it's when I multiply epsilon mu here. So it is N. Later on we'll use that, but for now it it doesn't matter. The omega over K, so you can write if you like. It doesn't have to be. This is there's a K over omega. So you can write the square root of mu, and then write this as a univector. Because the magnitude is K over omega, which is this one, and the rest is univector across this one, the same phase. Okay, so that is fine. And this is like 7.30. Jackson wrote it that way, except that univector Jackson just write out explicitly K divided by magnitude K. That's basically the same thing. Okay, so that's the incident wave. Now you keep doing it. The refracted wave on the other side. So we can basically exactly the same, except that you change to this pine called pine variable. This e pine is 0 pine e to the I in pine dot of x times omega t, and e pine is obviously just like this one. We have mu pine epsilon pine and k pine univector cos omega is of 0 pine, and the same phase factor. Okay, so that is not difficult. Now the refracted wave is the same. Double pi is e sub 0. Double pi e to the I 3 double pi dot omega t. So far so good. E double pi is now it's just the same as either this one or this, except that this is in the same medium as the incident wave is still epsilon mu. So now you don't have epsilon pi, double pi, and mu double pi. It's still just the usual mu epsilon, just like here. But the univector is the x k double pi. Is this k double pi in cos sub 0 double pi. Okay, the only difference is that this medium is the same as the incident medium. Okay, so but other than that, is the formula basically the same. Now we need to satisfy the boundary condition because you have interface between the two media, and the boundary conditions are from the Maxwell equation. So you have Faraday's law, you already have that, and you have divergence B is 0. Divergence D is also 0. because you don't have free charge. This is what we call, let's just consider wave propagation. And then you have the Ampere's law of H is positive. And there's no J term, no free current. And now we can again that these Maxwell equations translate to the boundary condition. Now, because the right-hand side for these two are 0, and these two are not 0, but then they are not singular function on the surface. So the jump between the two medium is still 0. So you translate to say like this one, you translate to a jump. Jump mean the quantity on one side minus the other, and for this case doesn't matter. It's because the jump is 0. It means that the right hand side and the left hand side should be the same. So you can just write this. But this one is just d dot n. I mean, you can put the jump outside because n is defined as vector. Now, normal to the interface, and that is you need to be a little careful again. Previously, we defined n as the propagation direction of the wave, but for this section, now you redefine your n as the normal vector between the two media. So n is basically this UV vector. So this is just this. Okay, and this square bracket meaning taking a jump over the two sides and near the z equals 0. So that is 0. Okay, and similarly, v dot n, the jump over v dot n is 0, and then the two curl becomes cos part of e, the jump of e cos n is 0. And then finally, the jump of h cos n is 0. Okay, so these are the 4 boundary conditions we need to satisfy. Okay, so the first application of the boundary condition is to derive these geometrical optics relationship. And that is actually easier because now we don't actually talk about a jump right away, because that later on we'll consider the jump explicitly, or I mean that all these amplitude vectors. So, but we'll just consider a phase, because you want to match them. You want the right hand side, left hand side the same. If you don't want to satisfy all these relationship or the boundary condition with these functional form, you always have a phase. But then you have different terms have different phase. Like on this side, you have 2 terms. You have this E and B, and the E double prime and B double prime. They have this phase and that phase. And for in the medium, upper medium, you have this E prime and B prime. They have this phase, right? And in order to match them, because the phase has this spatial dependency, and then obviously everything depends on time. The time is okay because it's all cancelled out, but then k dot x, your k dot x here, your k prime dot x here, your k double prime dot x. It depends on spatial location, meaning at different location, these are supposed to be different, because k and k prime and k double prime, they are not the same, right? Then in order to match the boundary condition, the first requirement is that all the phase should be the same. So we require the k dot x equals to k prime dot x equals to k double prime dot x. That is at the 0, 0. Okay. So Okay, so that's the application. Now the to apply the angle. I mean the apply this you take into account the of the angle, right? So basically, you consider x. Now x is just along the plane because you're matching a boundary condition on zero plane, so you can use this x is whatever coordinate you want to use, whether Cartesian or cylindrical, because you can both set the zero. So you use the because k is along this direction, so you might as well just say along the x direction and choose the y equals 0. Okay, so x in the x direction, right? So basically becomes k dot x is the magnitude of k times k dot x is the magnitude of k times the magnitude of x, which is just x, and then the k vector dot into the x unit vector, which is along to this direction. So x unit vector is here, the k vector is here. The dot product is the angle between them. So which is this is I, this is pi over 2 minus I. So it's cosine of pi over 2 minus I, which is the same as sine. So sine, right? And now consider this equals to that first, because this is in k double pi. K double pi is in the same medium, so we satisfy this. So omega over k is this one, but this is also equals omega over k double pi. The magnitude of k double pi is the same. So it's the same k, but this one is k. Now this sine, instead of this angle, is that this angle is this alpine angle. So immediately you see that the I equals to alpine. Okay, so you might as well change that to I. This is I. Right? You see that so this k double pi, the magnitude. I mean, you can use unit vector now because you pull out the magnitude. The unit vector of this one dot into the unit vector of this x-axis is the cosine of this angle. This is pi minus alpine. Pi over 2 minus, which is sine of alpine. But sine of alpine equals sine I, so I equals. Okay, so that's simple enough, right? And now the middle term, so that's equals to that. That has to be calculated. That equals to, now it's k pi x sine r. Just sine r. Okay. And now you can figure that out right away. So k is proportional here. K is omega times square root of mu epsilon, or in other words, you can use the refractive index of refraction. So k will be omega times n divided by c, and k pi will be omega times n pi divided by c. So both have the omega, the same omega and same c. So you have k here, k pi here. X is the same. So you combine all these. Just look at this relationship. So this is proportional to n. and so n times sine I is the same as n prime. But you see that's a k from this equals to that. So k is proportional, and the rest are the same for both sides, omega and c. So you see the n sine I is n prime sine I. So this is the Snell's law. That's okay. So this is you have learned that before in optics or general physics. General physics has a little bit of optics also. So this is the how you determine the refraction, the angle of refraction, and that is due to the difference in the index of refraction. Okay, so that is straightforward.